In this video, we're going to talk about alternating series. The main thing that you'll notice is that if you look back at some of the series that we've been talking about recently, and certainly the tests of those series, things like comparison tests and the integral test and stuff like that, these are all relying on the fact that the series that we're looking at, somewhere in the conditions, it says that the terms are all positive, meaning all of our partial sums keep getting bigger every time you add a new term. If you go back far enough, when we were first introducing series, that wasn't necessarily true. We had series, like some geometric series that bounced around with some positive terms and some negative terms and things like that. And so we're going to return to those. We're going to call them alternating series when terms bounce back and forth between positive or negative. We're going to introduce the alternating series test, which, as you can imagine, is going to be a test to see if a specific alternating series converges. We'll prove it here, which isn't going to actually be too bad. We just have to think about things in a little bit of a strange way. And then we're going to introduce this idea, this terminology of absolute and conditional convergence. And we'll talk a little bit about what the impacts of that are and what the implications are. So that's where we're at so far, and that's what we're up to. Let's get this rolling. First, an introduction to just what alternating series are. Here's a definition. This is not a super rigorous definition. Oh no, I got to fix this. I messed up my superscripts here. So let me write this, and then I'll fix this in your version of the notes. You can tell I'm not proofreading anything before I put it out, or at least into these videos. So here we go. If we have some terms of this sequence that are all positive for all k, then if we throw this little exponential here on it, then every time k changes, this is either going to be -1 raised to an even power or an odd power. And depending on what the exponent is, the answer is going to be either 1 or -1. So all it's doing is it's flipping the terms back and forth between positive and negative. Now, I wrote this as -1 to the k or -1 to the k plus 1 because it doesn't matter which terms go positive and negative. The ones where k equals 1, 3, and 5, or the ones when k is equal to 2, 4, and 6, etc. Most of the time, these alternating series are set up where the first term, whatever your index starts at, is positive. So if we started at k equals 1, maybe we'd have this -1 to the k plus 1, so we start with -1 squared, a positive thing. But it doesn't really matter. So you can see that in these two examples, right? Let's just write out some of the terms here just to make sure we can see what's happening. So when k is 1, we have -1 squared. That's 1 over 1. And when k is 2, we'll have -1 cubed. That's -1 over 2. And then we'll have plus a third, minus a fourth, plus a fifth, minus a sixth, plus, minus, forever and ever and ever. Really, really similar to the to the harmonic series, where it's just this series of reciprocals, but now we're going to call it the alternating harmonic series. Cool. And we've got something like this, where k can start at 0, and so -1 to the 0 is 1 over the square root of 1. Then we have when k is equal to 1, minus 1 over the square root of 2, plus 1 over the square root of 3, minus 1 over the square root of 4, plus 1 over the square root 5, minus 1 over the square root 6, plus, minus, blah, blah, blah. You can notice, hey, this is just another p series, except now the power isn't 1, it's half, and it's a little bit off, right? We could do like an integral U substitution thing to connect it to a p series, but it's pretty close. We could rewrite this as a p series, certainly, and it would go fine. Except now it's an alternating p series because, again, we've got these minuses, pluses, minuses, pluses going back and forth forever and ever and ever. So this just throws a little bit of a wrench into this. Let's first build some intuition before we move on and talk about the alternating series test. Hopefully, you can see that it's probable that these are going to have an easier time converging. Because now, instead of your partial sum growing and hopefully kind of reaching some sort of a limit, your partial sum is going to be growing and decreasing as you add and subtract things. And so it might be easier to reach some sort of a limit if you're bouncing around like this. So we'll have to see how that partial sum grows and decreases, but maybe it's easier to reach some sort of an upper limit if we're adding and subtracting, right? This is going to keep taking stuff away from our partial sums instead of having them grow unbounded too much. Now, it still might, but that's going to hopefully be a little bit easier for us. So the intuition, these little negatives in here, this subtraction of terms should hopefully do an okay job of making this converge a little bit easier. All right, so let's introduce the alternating series test. I'll give a proof of it. We'll look at some examples where we use it, all that kind of stuff. Here's the alternating series test. We've got some alternating series. I've written it as -1 to the k plus 1 a sub k. And remember, a sub k is all positive. It converges if the terms of the series are eventually non-increasing in magnitude. Okay, what the heck does that mean? We'll come back to that. And then, this is cool, if this limit of terms goes to 0. Well, wait a second. We've seen this kind of thing before. All right, so this is a little bit funky. Let's talk about this. First, let's focus on this non-increasing in magnitude. Magnitude is just the size of the terms without considering sign. So we've got positive and negative terms, but we really just want the size of the terms themselves to be non-increasing, or hopefully decreasing. What this means is that if we just look at the absolute values, now, again, we've defined these a sub k's to be positive, so we really don't need these absolute values here because these things themselves are positive. This is the thing putting positive and negative signs on them. But I'm just throwing in the absolute values so we really know what's going on. If the size of these things is going to be getting smaller, they're all bigger than 0, but the next term is smaller than the one before it, and we'll say that happens eventually, so after some index n. Most of the time it happens right away, but we could have something where a series gets really weird, and then eventually it kind of levels out. The way that we deal with that is just cut it up and take a look at the ending of it and say, okay, this is the part where we care about. That's the part that's going to tell whether it's converging or diverging. And again, we've got this limit going to 0. So first off, let's just be careful here. This looks like the failed case of the divergence test. The divergence test was the very first integral test that we found. And we said, hey, if the terms don't go to 0, that means your series diverges. And we said, if the terms do go to 0, we don't know anything. But now that we're not just dealing with positive term series, this alternating series test says actually for specific types of series where you have these positive and negative terms mixed in, every other term, like the way that we've got them, if the limit goes to 0 of the terms themselves, that is enough. Normally it's not. For a positive term series, it doesn't tell us a single thing. But for these alternating series, it happens to be enough to tell us that a series is going to converge. So if we go back and look at the alternating harmonic series that we had earlier, when k was equal to 1 up to infinity, we had -1 to the k plus 1 over k. And originally, when we looked at the alternating harmonic, the regular harmonic series, the one with just 1 over k, we said, well, sure, the limit as k goes to infinity of 1 over k goes to 0. Sure, that's true, but it doesn't really mean anything, right? We still proved that this regular harmonic series, this one up here, we showed that this diverged. We had lots of proofs for it, right? We did one in a video. I think I've got a paper, not mine. I posted a paper that goes over a litany of proofs that this series diverges. But here, the alternating version of it, if we add this thing in, then when we look at the absolute value, this gotten rid of the alternating part, just this a sub k, which for us gets rid of the -1 to the k plus 1 and says, well, whether it's -1 or +1, the absolute value is 1 over k. That sequence goes to 0, and so that is enough. So this series converges. The alternating harmonic series converges while the regular harmonic series doesn't. Oops, I wanted to erase, not highlight. So that's something a little bit weird. So this is the alternating series test. For alternating series, if the limit of the terms does go to 0, that's enough. All right, let's prove this. It's a bit of a weird proof, but oh well. We're going to look specifically at this version of an alternating series where all the terms are positive for all the k's, 1, 2, 3, 4, etc., etc., etc. And we're going to notice that all of the next terms are less than or equal to all of the beginning terms. Now, we said it was only needed that they eventually have this non-increasing stuff going on, but I'm just going to say right off the bat it's non-increasing. You can tinker with the proof and change it a little bit by cutting things up and blah, 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 but whatever. We're going to split the series in half, and we're going to look at partial sums. So we're going to look at even partial sums. The first 2 terms added up, the first 4 terms added up, the first 6 terms added up. And we're going to look at odd partial sums, the first term, the first 3 terms, the first 5 terms. what you're going to notice is that the only difference is going to be either like a positive or a negative term that's going to be added or subtracted on later. So anyways, let's start with looking at the even partial sums. Here they are. I just wrote some of them out. The S sub 2, the first two terms is, maybe I'll write up this series just so we can see it again. Ooh, that's a bad capital sigma. Let me fix that. All right, there we go. That's a little better. We've got this negative 1 to the k plus 1. Oops. A sub k. So when k is equal to 1, we have positive a sub 1, and when k is equal to 2, we have negative k sub 2. So we're subtracting these two things. Now remember, we said that this thing was non-increasing, which means this term here is smaller than a sub 1, right? We've got a sub 2 is less than or equal to a sub 1. And that means when we subtract them this way, we're guaranteed that the difference is going to be greater than or equal to 0. Cool. All right, if we look at the first four terms, then notice this was s sub 2, which is greater than or equal to 0. Sure. But also, we're adding on a sub 3 minus a sub 4. And just because of this difference being positive, because we have this non-increasing sequence, same thing is happening here. So this is s sub 2 plus some actual non-negative number, meaning s sub 4 is greater than or equal to s sub 2, because we're adding something here, not subtracting. And we can repeat this process by just looking at the next partial sum, which is going to be the original partial sum that we had, plus the next two terms, which the difference of those things is positive, or at least non-negative. And so we have this continual inequality, where when we look at the even partial sums, s sub 8 is going to be greater than or equal to s sub 6, and s sub 10 is going to be greater than or equal to s sub 6. And that means s sub 2n is going to be greater than or equal to s sub 2n minus 2, which is or not the original, but the preceding term in the sequence of even partial sums. So now we're considering this sequence, and what we've found is that each term is a little bit bigger than the one before it. So that means the sequence of even partial sums is non-decreasing. Cool. Specifically, we'll say monotonic. That's helpful. We can also notice that when we write out s sub 2n, the general term, the explicit formula for it, we're going to see, I shouldn't say explicit formula, the general term, sorry, we're going to see that it's bounded. So here that is. S sub 2n is just all of the terms added up until the 2nth term. But if I group them in this way, where I look at these pairs here, notice that if you factor out this negative and write them in parentheses, this is a sub 2 minus a sub 3, which is non-negative because a sub 3 is smaller, or at least equal, right? Because we have this non-increasing sequence of terms. And so this is a sub 1 minus something, minus something, minus something over and over and over again until eventually we just keep subtracting until this last term. So what that means is that s sub 2n has to be smaller than a sub 1 because we just subtracted off a whole bunch of non-negative stuff. All right, so there, we have an upper bound. So s sub 2n is monotonic and bounded. Bang, this thing has to converge. That's good. The sequence of even partial sums, we can say, converges to some number s. So we've got this limit, and we'll just say whatever that limit is, I don't really care. It's just a real number. We'll call it s. Cool. Now, that's not enough. We have this odd partial sum sequence that we haven't really talked about at all yet. So just having the even partial sums converge isn't good enough for us. But what we're going to try and show is that the odd partial sums also converge, and more specifically, they converge to the same number. That's going to be good. All right, so let's consider the odd partial sums. S sub 2n plus 1. Instead of trying to figure out if this sequence converges by doing the same thing that we did before, doing the monotonic boundedness stuff by playing around with terms, we want to show specifically that it converges to that number s, the same thing as s sub 2n. And this is not hard to do if we can wrap our minds around this fact, that the odd partial sum is equal to the even partial sum, the first number of even terms added up, plus the next one. Notice this even partial sum isn't just the even terms. It's the first however many terms where that number is an even number. So it's the first two terms, or the first four terms, or the first 8 terms. But that's not the second, fourth, sixth, and eighth term. That's the first, second, third, fourth, fifth, sixth, seventh, and eighth term added up. And so if we want S sub 9, just add the ninth term. Cool. All right. Now we can take a look at the limit of both sides. If both of these things are equal, then the limit should be equal. And we can split this limit up. And we can say, well, let's look at the limit of this partial sum and the limit of this term. Well, the limit of this partial sum, we already know. We found that earlier. And now we have to figure out, okay, what's the limit of this term? But notice the limit of this term, the odd term of this, that's the same thing as the end behavior of the whole sequence. And we said, hey, if this thing goes to 0, then this is going to converge as well. So what happens if this goes to 0? Well, if it does, then we have S, that's the limit from the partial sum, plus some 0 thing equals S. And so, since both of these sequences converge to the same real number, our series has to converge as well, because the regular partial sums are going to converge there. So all this relies on the limit of the terms being 0. All right, so as long as we have non-increasing sequence of terms in terms of magnitude, don't worry about the signs, and those terms approach 0 as n goes to infinity, then our alternating series converges. We don't have to know what S is in this case, what it converges to. We just care that it converges. All right, so let's think about absolute versus conditional convergence. This is some new terminology that we're going to introduce, and it really is only relevant when we talk about alternating series. I'll talk about why in a second. So if we have some series and the series of the absolute value of the terms, essentially the positive term version of it, converges, then we say that that series that we're looking at converges absolutely. And if the series itself converges but the absolute value diverges, then we say that the series converges conditionally. So here's what I mean. Let's take a look at this series of the absolute value of -1 to the k plus 1 over k. Now, the absolute value of that stuff, sorry, I'm writing kind of diagonally. The absolute value of that is really just equal to 1 over k. All right, the absolute value of the numerator is going to be 1. The absolute value of the denominator is just going to be itself because k is counting up from 1 to infinity, so it's already positive. Now, this is the harmonic series. This diverges. But we said the alternating harmonic series converges because the terms go to 0. So for this series, we can say this converges conditionally. Essentially what we're saying is, as long as we meet this condition that we've got the alternating version of it, right, then it's going to converge. If we remove that feature and we just look at the positive terms, it's not going to converge. We can compare that to this one. And for this one, let's look at the absolute value of these terms. You'll notice that that's only going to impact that exponential. So we've got k over k cubed plus 1. I'm not going to do the work for you on this, but I'm going to give you a hint. Use a comparison test to show that this series, the k over k cubed plus 1, converges. I'll give you an even bigger hint. You're going to compare to 1 over k squared. You can say k cubed plus 1 is bigger than k cubed, so that means that 1 over k cubed plus 1 is smaller than 1 over k cubed, so that means k over k cubed plus 1 is smaller than k over k cubed, which is 1 over k squared. This thing is going to be smaller than a convergent p-series. It converges. Done. But go ahead and actually write all that stuff out and see it. That means this series without the absolute values, oops, let me get rid of those. I keep mixing up my highlighter and eraser. This thing converges absolutely because the absolute value version of it converged. One last thing to talk about. and I've kind of implied this already, is that if your series converges absolutely, then the regular version of it converges, right? If the absolute value converges, then the regular version converges. So up here, we don't really need to test the alternating version of that second example because we did the absolute value version, the positive term version, and by a comparison test, we show that it converges, and so we're done. We can say, hey, this thing converges absolutely, we're good to go. Also, if the alternating version diverges, then the absolute value is going to diverge as well. So the main point, or the main kind of intuition that I want you to leave with, is that alternating series have an easier time converging. And so a lot of the time, we care about how that alternating series converged. Did it converge because it met a lower requirement, or would it have converged even if it wasn't alternating, right? Did it have to have this lower standard of convergence, this alternating series stuff, where that's the only reason it converged, like the alternating harmonic series? The only reason that converges is because it's alternating. Or was it a normal series that would have converged anyways, and then we just happened to look at it as an alternating one? So that's something that we'll keep an eye on, and we'll try and classify these as converging absolutely or conditionally. Normally, if you have a series that is only positive terms and it converges, then sure, the absolute value of it converges as well, because if it's already positive, then the absolute value is the same thing. But normally with a positive term series, we won't say that it converges absolutely. We'll just say it converges. It means the same thing, but it's just normally not a clarification that we make. We normally make this clarification of absolute versus conditional convergence with alternating series specifically. You can include this little qualifier every time if you'd like. If a series that's positive term converges, feel free to say it converges absolutely, but I'll probably just say it converges and assume that you know that that means absolute convergence because, again, the absolute value of the terms is the same thing if they're all positive anyways. All right, relatively short video, but there's not really much to this other than jumping into some examples. So hopefully you've got time and space to do that. If you want, I'll throw some videos up on Canvas where you can look at some other examples and see how things go. But this isn't too big of a topic. Good luck, everybody.